So what happened to Hong's solution? He had some camera and stuff. It's not better than that. Yeah, that's usual. Yeah. Alright, yeah, maybe we should start. So, okay, so today we'll talk, we'll wrap up linear programming and we'll start a little bit about impact. Okay, so that's the goal. And yeah, so the usual announcements. So as I said last time, homework 5 is out. And so the project Midway report, which I actually forgot to create the assignment on Canvas for it, but it will be there soon. Okay, so actually, you can do it, right? Can you create an assignment? Yeah. Okay, so we should do this. Okay, so it's due it's technically due tomorrow, but it's okay if you submit by the weekend, okay, because you don't. I mean, I'll probably take a look at some of them on the weekend, so it's nice if at least some of you submit by tomorrow. But the actual deadline will be. All right. And so, what did we see last class? So, we've been looking at linear programming formulations of various problems. Okay. And the interesting thing was we start off with discrete problems like shortest path or something, and we come up with these continuous optimization formulations of these problems. And we saw last time that you have a bunch of scenarios that could happen. Sometimes it could be that you solve this continuous optimization problem and you magically just get integer solution. In which case, this is great because you've actually found the right solution. But sometimes, but very often, you're not that lucky. So you end up with solutions that have some fractional values. And we said that even there, not all fractional values are created equal, right? So in the sense that sometimes you could have solutions that are somewhat integral, okay? That, like you have values that are pretty large and values that are pretty small, and there you can somehow round them up and down so that you get some good approximation algorithms at the end. We saw two techniques. One is just based on some thresholds, and another is based on what's called probabilistic rounding, which we also call randomized rounding. And for some problems, in particular, we saw this example of independent set, where moving to a linear program was made it completely useless, right? Like you could always get, even for a clique where the independent set, the optimal independent set has size only one, the linear program was thinking in some sense that the maximum independent set was of size n by 2. Set everything equals half. The constraints value. Okay, so this can sometimes happen, right? So in practice, if you write a linear program, this could happen that you just get a totally useless value, and often that means that you need a better linear program. So that's what we saw last time. And randomized rounding is an interesting idea to keep in mind because so ultimately, this whole business of rounding, you have to think about it as you solve an optimization problem and you get a fractional solution that's supposed to tell you something about the optimal integer solution, right? And how you move from that fractional values to the integer thing is the whole game. Okay? And randomized rounding is a natural thing where you say, I want to round to 0 or 1, I get some fractional value between it, and I just round it up to 1 with probability equal to the value. So if your value happened to be 0.7, then I round it to 1 with probability 0.7, and to 0 otherwise with probability 0.3. So that's randomized rounding. This is a very powerful paradigm. Okay, so this is often used for routing in networks and so on. So for like a bunch of graph problems where somehow you don't want to, which happen to be intractable, sometimes you just solve the linear program and you do some randomized routing, and it works very well. Okay, so this is actually the original paper in which randomized rounding was introduced. So it's just for those who are interested. Okay, so this is. Okay, so this, this is interesting reference. Okay, so this is a quick summary of what stuff we've seen so far. Yeah.
Let's say last time we say it's bigger than 0.5, it'll make 1. Otherwise, it makes 0. So is it saying us, just choosing a fixed threshold?
So there's no randomization, right? Because you're deterministically rounding everything over half to 1 and everything less than half to 0. Okay, so this isn't randomized rounding, but you could have a more sophisticated randomized rounding where you say if it's more than half, then I will round it with p by 2 or something like this. If it's less than half, I never round it to 1. Okay, so you could have more complicated randomized rounding schemes. And sometimes there are these rounding schemes that are based on like looking at joint distributions where you round like 2 variables at a time. So, okay, so there's all kinds of stuff there, but we saw the most basic version. Yeah.
Is this rounding in any case useful for non-zero one discrete problems?
Yeah. Actually, I should have given at least one example of such a problem, but I didn't find anything that was like easy enough. Okay, but there are many problems in which, some of the problems we have, you could have initially phrased it as variables that are not zero. Right? So the question he asked is, so far we've just been looking at 0, 1 problems, right? Like you have been looking at variables being 0 or 1. You could have, for example, assignment variables. Right? So I think we saw this scheduling problem where you have to schedule a job to one of m machines. That's one example. Or you could have placing objects on a line, something like this, where you want to place them on integers 1, 2, 3 up to n. So for these kind of problems, you might imagine that you write that the natural variables will actually be some fractions in a range. Okay? And then maybe you want to round to the closest integer. Okay? So usually that turns out to be a bad strategy. Okay? So you might be much better off. So if you have variables in a discrete range, variables that take values 1, 2, 3 up to k, you might be better off having k different variables. Okay. So this is, let's say, xi belongs to this. Might be better off having k variables which I call yik or yik. So these are 0, 1 variables, and this is equal to 1 if xi equals j. Okay. So you might be better off introducing new variables which are Boolean, okay, and which have the constraint that sum over j of yij equals 1. Okay. So sometimes for many problems, this kind of things are better than just having fractional values in that range. Yeah.
When we say we have a solar, just a manual solar drilling programs that's following the polynomial with respect to the number of units you put in on
Yeah. So okay. So this is something I was hoping to hide under the rug, but since you asked for it, you get a complicated answer. So yeah, so the running time of linear programs is actually a slightly tricky thing, and so we said that it is polynomial time, right? So okay, so maybe I should mention. So since we've seen something like this before, I don't think this will come as too much of a shock for you. But so this is polynomial time in the size of the linear program, right? In the size of the linear program. And what does this mean? This means that this is the total bit complexity in writing down value. Okay, so if I have a bunch of constraints, okay, so if I have like maximize C transpose X subject to okay. So yeah, so what is the bit complexity in writing down C? Do you guys remember we saw this like very early in the class? Some of you were intrigued even then. So what is the bit complexity in writing down C? Shouldn't review these finals, but these kind of things are useful. Okay, so the bit complexity is basically it's the amount of space you need to write down the C. Okay, and you might think that C is just a vector of n things, so it is a C, but note that these are n real numbers, right? So you have C1, C2 up to Cn. Okay, and each CI could have some. It will have something like if they are integers, they would have something like log of Ci base. In general, there could be some fractional things, in which case it is the number of binary things, the number of bits in the binary representation. And so you count these. So these are the number of bits you should write to the C, and you do the same for the A, the B's, and so on. And that is defined to be the total size of the linear program. Okay, so it's at least as big as the number of constraints plus the number of variables, or even number of constraints times the number of variables, perhaps. Okay, because each AI has n things, and there are m such AIs. But it could be much larger. And so, in particular, an interesting corollary of this is that we don't know if solving a linear program of the kind square root of x plus root 3y plus pi z or something like this. If you have a variable, I mean, if you have constraints like this, none of our polynomial time algorithms actually, imply anything. But of course, you could say, if the moment you truncate this to some appropriate value, you are in good shape. So this is so this is a slightly tricky thing, and in fact, finding an algorithm that is only in So this is a big open problem. Okay, so this is called finding strongly polynomial dynamics. Okay, so finding this is actually a big open. We don't know if it's possible. So, all right. So that's yeah. Actually, this relates nicely to what we will see later today, which is about how the model is important when you're talking about time complexities and so forth. Okay. So yeah. So anyway, so this is the quick outline of time complexity of solving linear. So you can, in practice, you can usually solve them efficiently, and it is basically number of constraints times number of variables. But that's only because the C's are often of like bounded size. Yeah, and also there are all these questions. Like when you're actually solving a linear program, there is this question of how much accuracy you've got to keep, right? Because, and this is often, I don't know if you have encountered these kind of problems before, but like in some learning problems and in some numerical analysis problems, often the accuracy to which these intermediate computations have to be kept is very algorithm dependent. Okay, like if you do Gaussian elimination in a naive way, you might end up with very, very long vectors and things like this. Very, very long numbers and things like this. Okay, so these numeric precision issues show up a lot when you're talking about linear. So yeah, but this is all very messy. This is why nobody talks about this because it's probably yeah the usual right. Effort to reward ratio is very small. So studying. All right. So that is this. That is what we have seen. Okay, so I wanted to end with another cool thing about linear programming, which is called duality. Okay, and I want to motivate this as follows. Okay, so this is a very important property of linear programs that has a lot of uses. Okay, so let's start with a very very basic example. Okay, so suppose I want to argue about the optimum of this linear program without actually solving it. Okay. Now, staring at this linear program, can you give me a lower bound on what the optimal value can be? So, can you say that off is at least something? I mean, I just want to say I don't know what opt is, but opt is at least one. Okay, so can you give a bound like this? Yes. Yeah, excellent. Okay, so if you just add these two constraints, right? So you just get exactly that x1 plus x2 plus x3 is bigger than or equal to 10. Okay. So this is this might sound like I mean it's a very specialized operation, right? Like I clearly arranged for this to happen. But 1 plus 2 implies that x1 plus x2 plus x3 bigger than or equal to 10. So what we're saying is that sometimes you can manipulate these equations around, and maybe you get some bound on the optimum. And I tried finding an example where you don't quite get the right bound, but it was a bit tricky to do. Okay, but sometimes you can get some bound by manipulating equations, but it may not be like the tight bound. I mean, there may be one way of manipulating that gives one bound, which is not so great, but maybe there's a cleverer way that gives maybe the best bound. Okay, so you can find examples of these kind of things. Okay, so yeah, but the interesting thing is that you could come up with this without actually solving the program. We don't know if this is actually the optimal solution. So we just know that this that the optimum cannot be less than 10. Yeah.
What is it? One.
No, I'll come to that. Yeah. So this is a toy example just to motivate us. Okay. So yeah. Yeah, I should have said this. Okay. So all right. So this basic example is clear, right? Okay. So let's now ask this general question, right? So can we try to formalize what's going on in this kind of manipulation? Right, so suppose you have a more general set of equations where your problem is to minimize C1. I'm going to write this down just so that it is a bit easier. C1x1 plus C2x2 xn subject to A11. Okay. So in general, you have a linear program like this, right? So you have a bunch of constraints. And when can you conclude that by there? Like what exactly happened in this previous example that led us to conclude this? Can we try to pinpoint that? Yeah.
The extremes were, all of them were bigger than certain number.
What do you mean they were bigger?
I mean, each constraint was greater than some number. And we were looking for the maximum. And then we added enough, and we like
Lower.
lower.
Yeah. So yeah, that is true. So I guess what you're saying is that somehow when you added these things up, we ended up with exactly an equation that C is bigger than or equal to something. Okay. But what does that mean? Like in terms of the coefficients, the A's and the C's, what was going on in that example? Like, would it have happened if my coefficients were, if I had an extra x1, right? So if I had an extra x1 here, maybe I should write a different color. If I had an extra x1 here, if I added these two, right, then I would have got something that said 2x1 plus x2 plus x3 is bigger than or equal to 10. And note that this is a totally useless equation if I need to argue about x1 plus x2 plus x3 bigger than or equal to 10, right? Unless I knew x1 was positive, something like this, x1 was negative, something like that. Right? So there was some luck involved here. And so can you try to formalize what exactly is happening? Yeah. Yeah, so it's not just a linear combination, it was precisely the sum. Right? We'll get to this in a bit, but yes. So in the previous example, so each Ci was exactly A1i plus A2i plus AMI. Okay, so you added up the coefficient of xi in all of these equations, that is exactly equal to Ci. Okay, so this was a coincidence, right? So this is why you got a bomb. So do you really need this, or is, as you're saying, is some linear combination enough? Like if can I add these? So essentially, I'm asking, what if I add these equations up with some coefficients, right? Like I can take. So is there any bound on? I mean, is there anything that we should ensure about the coefficients? Can I take the first equation, let's say, minus the second equation? Right, so you can't multiply by negative numbers, right? So you can always say that if the first equation is valid, then 2 times that first equation is also valid. Because if you multiply each AI by 2, it will be less, it will be bigger than 2 pi. But if you multiply by a negative thing, then the inequality switches, right? So you get a less than equal to. And that's no good because you can't add a bigger than equal to and a less than equal to thing, right? So what you can say for sure is that if you pick any yi's, so let's say I take a multiplier y1 for this equation, y2 for this equation, and ym for this equation. Okay. And suppose we ensure that yi is bigger than or equal to 0 for all that. And now, what is the coefficient that you've got to satisfy? So what is the constraint that like what would be the analog of the C equation? It would be the same thing but with the y's corresponding. So now, if we happen to have Ci to be equal to A ym for every I. Then we can conclude that the optimum is bigger than or equal to b1 by 1 So, would you guys agree with this? Because I'm saying that suppose I multiplied the first equation by y1, which is positive, second equation by y2, and so on, added them up. And suppose luckily the coefficients just turned out to be exactly c1 for x1, c2 for x2, and cn for xn. Then you can get a lower bound on the optimum, right? Because that's a minimization problem. You want to see how low it can get. And so this would say that b1 by 1 plus b2 by 2 plus bm by m is actually a lower bound for this for the optimum. Okay. Right? So everyone's here for fun. So now you can ask the following question, right? Like suppose I gave you a bunch of equations. You could now ask, can I manipulate these equations to get that thing to get sum of ci xi bigger than or equal to a certain quantity? Right? Like so if I gave you some arbitrary bunch of equations, how would you check if there exist multipliers like this? So I'm flipping the question now, right? So initially I said that suppose I knew a bunch of y's such that when you added up these equations with multiplying by y, you get exactly that thing bigger than something. Then you had a load. Now I'm asking the next question, which is I just gave you a bunch of equations. Suppose I gave you a bunch of equations. Then how do you do what she had done, right? Like find some multipliers so that you get exactly the equation. So yeah, so the question is, given the C and A1 transpose on to AN transpose, how do you find the Y? For instance, in this example, we said that initially without the plus x1, there actually existed some y's, right? Like y1 equals 1 and y2 equals 1 was a valid way of combining these equations. But the moment you had this extra x1, there was no valid way of manipulating these equations to get what you want. Okay? Now, in general, suppose I gave you something that looked more complicated, right? Like suppose I asked you to maximize like some 10 variables and right time, but suppose I just said x1 plus x2 plus x3 plus 2x4 and sorry, minimize. Subject to like 5 or 6 different constraints, right? Like suppose I said 3x2 plus 1 and a bunch of constraints like this, right? So how would you in general find out some coefficients without trial and error? Right? Like suppose you have lots of these equations, so clearly trial and error is not possible. So how would you see if there exist y's that are positive so that you get something? Yeah.
You could write the linear equation.
Right. So one thing you can observe is that what do I want these y's to satisfy? Right? So I want these y's to satisfy this equation for every I, and I want the y's to be positive. Okay. So to check if there are y's so that this thing happens, I just have to solve this linear system of equations, like y's that satisfy this equation for every I. Actually, maybe I should try for every I in the range 1 through n. So if I somehow find y's that satisfy these n equations, which also happen to be positive or non-negative, okay, some y could be 0. Okay, so then I would be in good shape. Yeah.
Would it be N or N?
It should be n. That's why I wrote it. N. Yeah, because there are n variables, right? So each ci was the coefficient of xi. So makes sense. Yeah. So that's why I was pointed out. So yeah.
So is this like something like linear regression?
Yeah. So what is this, right? So that's what we want to ask, right? So given C, how do we find I? And what we are saying is, all we need to do is we want to find some set of y's such that yi's such that yi is bigger than or equal to 0 for all I in 1 through n. So note that there are n different yi's, one for each of the constraints, and for every maybe I will use a little bit different letters. Maybe for this I will use yj. I see why his confusion came up, so maybe I should be a bit more careful. So yj says that yj is bigger than 0, and for all j in this 1 through m, you want this constraint, and for every I, we want Ci to be equal to sum over j Ai j Okay, so this is just notation, so I'm just writing the same equation. Okay, so all right, so this is what we have. All right, so this is what is this, right? Like, how would you find if there exists y? So he suggested some linear regression type thing, right? You want, but no, this is just exact equality. So you want y is bigger than or equal to 0. Is that this is yeah?
Well, so going back to the case where we had our one eyes already, right, when you multiply it with the y vector, use the A transpose matrix.
Uh-huh. Yeah, so there is a way of writing this in matrix form that I agree. Right? So, but what is this, right? Like, suppose I just told you find y such that this is true.
It's just another linear program.
Yeah, so the point is that this is just another linear program because here you have equalities instead of inequalities. But that's fine. You can always write an equality as two inequalities: ci bigger than or equal to this and ci less than or equal to this. Okay, so there's nothing special there, right? And so and you have these yj's bigger than or equal to 0. And all you're asking is find a feasible solution yj to this linear program. Like geometrically, you can each of these constraints is like a plane, and you have this intersection of planes, and you have this constraints about yj's being bigger than or equal to 0. So the point to note is that these things just another linear program. Okay, so the constraints we want these y's to satisfy are just none. All right, so now this is a linear program so far without an objective value. Right? Like this is just find me some feasible set of y's. Okay? But what might be a reasonable objective value given that, remember, our lower bound for the optimum of the original program was this b1 y1 plus b2 y2 up to bm yn, right? So if some values of y satisfied these constraints and you got some lower bound here, okay? So this is saying that whatever the opt was for the original program, it better be more than equal to this value. But you may want to actually find an even lower bound, right? Or no, sorry, an even higher lower bound, right? Because so for some values of y, it's saying like, so we have this origin. Let's say this is a real line. The true optimum of the first program was something like this. And if you use some y's that happen to satisfy this equation, maybe the sum of bi yi was this value. This was b1 y1, bn. And of course, this opt is bigger than or equal to that. So that's what that's what we just saw. So the manipulating the equations tells you that opt is bigger than or equal to this, which means it's on the right of this. Now, ideally, you would want to find a better low bound. You may ask, can I choose different y's so that sum of bi yi is actually even more to the right? That would give me a better lower bound on the optimum. I mean, it's like saying if your optimum is 10 or something, then maybe your first lower bound told you that manipulating equations in a certain way said that the optimum is bigger than or equal to 5. Now you would want to say, you would want to ask, is there a way of manipulating my equations so that I get the constraint that the optimum is bigger than or equal to 8, or even bigger than or equal to 10, in which case it would actually be the true optimum. So this is something you could ask. Okay. And the point I'm trying to make is that you could now throw in an objective value for this new linear program, which basically says maximize sum of bi y. Okay. And that would be like saying, find the best lower bound, find the largest lower bound that you can get using this manipulation procedure. Okay, so this is the thing. So the question is, what is the best possible manipulation? Okay, so that's what we want to ask. Okay, so we want is what is the best manipulating the constraint? And by best possible, we mean one that gives the largest value of sum over bj. Okay, so this is what we want to ask. Okay? And now this is now a new linear program with constraints being what we wrote down here. Constraints being uh, these things, yj bigger than or equal to 0, and this being these two. And you now want to maximize. Uh, so you want to so your new linear program is maximize b1 y1 bn y1 subject to y I bigger than equal to 0 or y bigger than equal to 0 for 1 and ci equals sum over okay. So this is a new linear program, and the cool thing is that if you take any feasible solution y to this linear program, then the sum of bi by I will give you a lower bound on the optimum. And this linear program is trying to maximize that quantity, which is in some sense saying I have this procedure for getting lower bounds on the optimum. What are the best possible coefficients? So that's what this linear program is trying to do. And this program is called the dual of the original. Okay, so yeah, so this is what so this is called the dual of the original. And now if you have the willpower, you can take the dual of this by doing the same procedure. Like these are equal, so you've got to replace them by two inequalities, and then you write down the best way of manipulating these things. It turns out that you get the original. So that's this nice fact about dual. The dual of the dual is actually the original program is called the primal, and this program is called the dual. The dual of the dual it turns out to be the primal. Okay, so this is a nice fact. So yeah, that we will not go into here because it's more it's easy but algebraically messy. So let's not do that. Right? But this is the cool thing about dual. Okay, so you try to manipulate equalities and manipulate the equalities in the original program, get a lower bound, and you try to write a new program that tries to capture how best this procedure can perform. And that's the dual. And we just proved the fact that we just proved, which is yeah. So maybe I should write down some shorthand because this will also help you in thinking about the dual. So remember for the primal we had a clean form, right? So and dual. Okay, so the primal has this nice form of minimize C transpose X subject to A1 transpose X Pm. So the dual, the primal variables were x1 to xn. And the dual, the variables are y1 to yn. Where m is the number of constraints in the primal, right? Because these were the coefficients. And now your goal, now the dual is a maximization problem. Max of B transpose Y. Right? B transpose Y, sum of BI1. So subject to so here it's just the same thing. Okay, so this is a little bit more messy because now you want the sum of the. So these are not. So remember, I said the AI transpose were the rows of this matrix. Yeah. So let me write this as a matrix so that it's nicer. So these constraints. Okay, you can build a matrix capital A where this is n and this is n. The rows of this matrix are these AI terms. So that's that. So that's the matrix A. And now the dual, and these constraints you can now write as A times X is bigger than equal to. So A times X is now a vector. Okay, it's a vector whose entries are all these left-hand sides. Each left-hand side is a number. So so that's this. And when we say a vector is bigger than or equal to another vector, we just mean entry-wise. So you can succinctly write this set of equations as this. Then it turns out that the dual has a simple form, which is A transpose Y is equal to C. And of course, yi bigger than. Okay, so this is again, this is nothing deep. It's just I want to say that in matrix form, the primal and the dual have like a very clean way of writing. Okay, so yeah, if you think about this a little bit, this is just restating what I've stated before, but in matrix form. Okay, so there's nothing deep. All right. So let me mention what weak duality is. So this is exactly what we have argued with before, which is that let Y be any feasible solution to the dual. Then B transpose Y is bigger than or equal to of the prime. Yes, this is by notation. So like of subprime. So this is exactly what we have argued, right? This is how we even came up with the notion. Because we said take any y's that satisfy these equations, then B transpose Y would be a lower bound. This is how we came up with the. And this fact is called weak duality, and this in particular implies that opt of dual. So if it is feasible, okay, so you can't write the word opt of dual if it's not feasible. So this is bigger than the problem. So this is So if you don't have to care too much about this. Okay, but if the dual has at least one feasible solution, okay, then the optimum of so for any feasible solution you have this B transpose Y is bigger than or equal to opt of primal, and okay, maybe the reason you guys are all confused because I have the opposite. Okay. Okay, so this is actually great feedback because I realized why all of you are. So, okay, sorry. Okay, so yeah, so we have B transpose Y is always less than equal to this because that's how we derive. So again, going back to this number line thing, right? So this is the set of this is just real numbers. Okay. So intuitively, how do you think about this primal, right? So primal has some optimum. This is the optimum for the primal, and the primal is a minimization problem. Minimize C transpose X. So there'll be some X for the optimum X for which it will achieve this opt of primal. For every other feasible X, maybe this is one X. For some X you get this value for the objective. For some X you get this value for the objective, and so on. So the primal takes values that are on the right. Okay, so for any X, the value of the C transpose X would be something on the right of that object. But now, on the other hand, if you look at the dual, what this inequality is saying is that any feasible solution to the dual will be some value on the left side. Okay, so this dual value for any feasible y, you get some point over here. So the dual values will be something over here. Yeah. So they are not the same problem, right? Because the way we define them, we said that you try to manipulate the equalities of this and get a lower bound. Okay? But we don't know that there is a way of manipulation so that you actually get the exact optimum, right? Because maybe all you get is that the optimum is bigger than or equal to, maybe the best way of manipulating these equations told you that the optimum is bigger than or equal to 8, whereas the true opt could have been 10. This is still consistent, right? Because there is no counterexample. So far we don't know this stuff, right? But it turns out what you're saying is also true, okay? And that is called strong duality. Okay, so for linear programs, it turns out that something called strong duality is true, which is saying that there actually exists a pair x and y, so that so strong duality says that I will write a condition which will is that suppose the primal and the dual are both feasible. This means that there's at least one set of one x that satisfies all these constraints. There's at least one y that satisfies all these constraints. That's what I mean. And suppose when both feasible, then opt primal is actually equal to opt dual. So going back to this line, it means that there is some feasible x. So this part we know, right? So there is, if the opt primal is the opt primal, then there is some feasible x that attains this one, unless that opt primal minus infinity. Actually, that also goes with one constraint. Yeah, both feasible and opt primal is finite. If it's negative infinity, then you can't say anything. Okay, then all bets are off. So yeah, so if it's finite, then there will be some x that would attain this value of optimum. But what strong duality is saying is this non-trivial fact that there is also a y that attains the same value as optimum. So so if you try to find the best possible y, there is some y for which you actually get this one. So in terms of our manipulating equations, this is like saying that there is, if I gave you a bunch of linear inequalities, there is always a way of manipulating these inequalities so that you can actually certify, so that this manipulation gives you the best possible outcome. Okay? So informally, what they're saying is, okay, so there is always just to conclude that is bigger than or equal to the true value, right? So that yeah, I don't want to write the octprimal is bigger than or equal to the octprimal because that's not what I want to say. So to conclude that. mm, the optimum of the primary program, primary P, is bigger than or equal to the true optimum. Okay. So this is an informal statement. So I just so treat it as informal, right? So what I'm so try to understand what I mean, right? So what I'm saying is like there is always a way of manipulating these inequalities, which means I can always find some y's such that if you manipulate and you end up with C transpose X bigger than or equal to something, you end up with C transpose X bigger than or equal to the true optimum. Okay. And that is, in some sense, a non-trivial fact. So, and no, this is, I feel this is the cleanest way to think about it because it's, so it's like saying that there is, you can think of each possible Y as a certificate that says that the optimum of the original program was bigger than or equal to something. Okay. And what strong duality tells us is that there is always a certificate that actually says that the optimum value is bigger than or equal to the true optimum. Okay, so yeah, so think about this for a little bit. Okay, so that's maybe I didn't quite say it right, but this is what strong duality does. Okay, and this is so that's why this is a non-trivial fact. But yeah, in terms of these inequalities, this is what it says. Okay, so you try to write down this program, and the optima of these two things are equal as long as they're feasible. But this intuition is always nice to do. So you will see. I mean, you'll see a couple of examples of this in your homework. You kind of drive this point home, right? Like you will choose some bad coefficients, and then you won't get the right optimum. You won't get that this B transpose Y is C transpose X is bigger than or equal to the right. Okay, but then you'll see that there are actually specific choices of Y's so that you can actually show that it's bigger than the true optimum. Okay. So yeah, so that's the nice that's the nice thing, and this is what is called strong duality. Yeah, so unfortunately, yeah, most textbooks just state it as this fact, like this is the primal, this is the dual, and the values of these two are equal. But I don't think it. But I think the right way to view these things is as manipulating equalities and trying to prove those. So that's this is one way to think about that. So let me tell you what are the applications, right? So far it seems like a mathematical exercise, right? So I told you if you have a bunch of inequalities, you can manipulate them with some nice properties. But one cool thing is that sometimes it allows us to solve exponential or even infinite size linear problems. Okay, because maybe not solve, but at least say that the optimum cannot be smaller than something. Right? So imagine a linear program like this, where m was infinite. Okay, and you wanted to say that the optimum is still bigger than or equal to some value. Let's say optimum bigger than equal to 10. Now all I've got to do is try to find a small subset of these infinite set of things. Okay, and depending on the application, maybe there is a way of finding them. Okay, where if I add those guys up, the right hand sides add up to 10. Then I would be done, right? Because then we are saying that then doesn't matter what these other equations are or how many there are. This would certify that the optimum is bigger than or equal to 10. Okay, so that is one very nice application of duality. Okay, so sometimes you may be able to solve exponential sized programs if your dual is something nice to reason about. So that's one thing. And the other thing which happens more commonly is that you have a complicated linear program and then you write down its dual. You realize that now you have some clean combinatorial structure. You can solve this program pretty fast. So this often happens. I'm trying to think of a good example. So for many cut problems, if you write down the dual, it turns out that you'll end up with like a shortest path problem, something like this. Okay, so that's that's one of the nice things. And the final application is that duality can be used sometimes as a proof technique. It's like you want to show that two combinatorial objects are equal, because we know that the optimum of the primary program and the optimum of the dual program are the same. You can try to say that problem 1 maps to this linear program, problem 2 maps to this other linear program, and these two are duals of one another. It sounds like too much coincidence, but there are cases in which it happens. Okay, like flows and cuts are one example, where you can write down the linear program for max flow, LP for max flow, turns out to be the dual of the LP for min cut. Yeah, again, this is ST and this is ST. Okay, so you want the maximum flow from S to T, and remember min cut, you just have to remove as few edges as possible. Right? So it turns out that if you write a linear program for max flow and you write a linear program for min cut, and these should be the appropriate linear programs, okay, then these two turn out to be duals of one. Okay, so this is so this is something that it's a little tricky, so that's why I don't cover it, but this is a good fact to know. Okay, so this is something. It's one of these things that takes half an hour of manipulation to see. So we could do it, but it won't be that insightful at the end. Okay, so it's a nice fact. All right. So what have we seen so far about linear programs before we conclude? So I said that these are effective ways to capture many problems. Okay, so you can write down linear programming formulations for many problems. First, you write it down as optimization, and then you change these integral constraints to 0, 1. Okay, or you change the 0, 1 constraints to this range xi lying between 0. This is what we can see. And sometimes you have somewhat integral corners, leads to approximation algorithms. The other thing that I mentioned is that LP solving is fast. One thing to note is that it may be very tempting to write down any problem you see as a linear program, but it doesn't work too well in practice. Okay, it works if your problem is reasonably sized, and most of the LP solvers we know maybe work if you have like 100K variables slash constraints, but they don't work if you have like a billion variables of constraints. So this is something to keep in mind. Okay, so linear programming is used often as in some sense a medium for problems of medium size. So, like in practice, often if you have like a very large thing, you don't want to run a linear program on the whole thing. You may want to break it up into pieces. Yeah, you may want to break the problem up into pieces. Maybe run something like a linear program on these smaller pieces. And so on. Okay, so this is something people often do with some distributed value. Anyway, so this is something to keep in mind. It's very powerful, but it's not powerful enough that you want to use it for any problem. All right, so that's a quick summary of linear programs. I think we should maybe start the next topic next time. I want to talk a little bit about interactability. We can end here, but do you have any questions? Right, so yeah, so let's stop here. Because the next thing I want to start is some sense limits of efficient computation, and we want to yeah, so next time we'll see questions like this. Okay, so far we've been focused on finding more and more efficient algorithms, right? And the question you want to ask is, are there limits? Okay, and this is what we'll continue to ask.